And here is Johann Thiel from CUNY.
All right, so thanks for putting this together. And thanks to all of you for coming, and those of you out in Zoom land, thanks for watching as well. So my name is Johann Thiel, and this is joint work with David Bradley from the University of Maine on generating functions for maximally expanded alpha trees. So we need to get to the definition of what is an alpha tree. So I need a couple of things here to get us started. So given a directed planar tree, we can label the leaves of our tree with one of two symbols. There's the bar symbol and the circle, but you might catch me later on just simply saying like O and 1, because I think that's sort of the easiest thing. We're using the notation from a previously established paper. So I'm sticking with their notation, but you might hear me describing labels as zeros and ones rather than circles and bars. So we can label the leaves of these directed planar trees. And so these labeled trees can be associated with some word in a language that only has two letters, right? The circles and the bars. And so what does it mean to have an alpha tree? If you give me a word alpha in this alphabet, an alpha tree is a directed planar tree that's associated with the cyclic conjugacy class of alpha and has a couple of requirements. Namely, this tree there has to be at least one internal vertex. Every internal vertex has to have at least one outgoing edge, and you cannot have a vertex with one incoming edge and one outgoing edge. So these are some restrictions that define what an alpha tree is all about. And so here is an example of an alpha tree with the labels, so that an associated alpha word here is 0011. Right? So that's an example of an alpha tree. And two of my colleagues at CityTech, Poirier and Tradler, were studying these alpha trees and how they're associated with these cell complexes known as an asocoipahedron. And yes, I did have to practice that a few times, and I am not sure what it means, because the two of them, they're topologists. And so they have these alpha trees that they've associated with these shapes. And David and I are number theorists. We came in a little bit later on this idea of trying to help them with counting. So we didn't actually need to know what these cell complexes are in order to do that. But that's the application. So if you're wondering what is the application for these alpha trees, there is one. It's by some topologists. I don't know that side of things. Okay, so some more definitions that we need here. We need to get to the maximally expanded part of the title. So if you have two alpha trees and one of them can be obtained from the other by taking two of the vertices and just collapsing them into each other, then we say that we have this association with them, right? We have this notation here, essentially that one contains the other. If you could do this by contracting a non-negative integer number of edges, then we have this association between two alpha trees that go with the same alpha word. And a maximally expanded alpha tree is where you cannot expand things anymore. There's no collapsing, right? If you try to take a vertex and sort of spread it apart and maintain the rules of an alpha tree, it just cannot be done. So that's what we mean by a maximally expanded alpha tree. Okay, so here are some examples of maximally expanded alpha trees for the same word that we had before. So if you go back, right, here was my alpha tree that I gave you as an example. And then these two are maximally expanded because if you take some of these edges, like for example, if you collapse this edge together and you collapse this edge together, you'll get the alpha tree that I showed you before. Same thing with this one. If you collapse this edge and you collapse this edge together, then you get the alpha tree from before. And these two are such that you cannot do the expansion anymore, right? You're out of options. It really comes down to the fact that these vertices have very specific forms that if you try to insert an edge in there, you'll break one of the rules that defines what an alpha tree is all about. All right, so those are examples of maximally expanded alpha trees. And so, well, I have to show you that maximally expanded alpha trees exist whenever there is an alpha tree. So what's one of the things that we worked on here? If I give you an alpha tree and you take an internal vertex of the tree, we can define the count of the number of incoming edges to that vertex, I of v, the count of the number of outgoing edges, O of v, and then this statistic, S of v, is the number of incoming plus 2 times the number of outgoing minus 4. So this is a statistic that we associate with every internal vertex of an alpha tree. And then if we simply sum that statistic over all internal vertices, we say that's S of t, that's the statistic for the tree. And so the question might be, maybe you're wondering, like, why am I doing that? Why are we doing this? Well, it turns out that this can help us determine whether or not a tree really is maximally expanded. That statistic is zero, is non-negative, and it's zero if and only if the vertex that you're looking at has either two outgoing edges or two incoming, one outgoing. From that, we get that for any given alpha tree, that statistic is negative. And then if you have two trees that are related by these expansions, whenever you expand a vertex and you insert an edge, that statistic goes down. And it goes down by 1. So every time that you insert an edge and you create a new alpha tree, it goes down by 1, which means that an alpha tree is maximally expanded if and only S of t is equal to 0. So you can take a look at your alpha tree, you can compute the statistic for the internal vertices, add all that up, if that's non-zero, then you should be able to expand it in some way in order to get it all together. And if you go back to the examples that I had before, right? So this example, there's this internal vertex, and if you compute the statistic for it, you see that there are 2 incoming, 2 outgoing, so that's 2 plus 2 times 2 minus 4, right? So that's not 0. This thing is not maximally expanded. Therefore, there should be some kind of expansion out there that lets you get to a maximally expanded alpha tree. And if you try to do the same thing for these two, you'll see that every single one of these is the statistic is 0 for all of them, which goes with that proposition that I showed before. They all have really what it's saying is that alpha trees, the internal vertices, can only have 2 forms, either this form or that form. If you have any internal vertices that look different, that have something else, you should be able to expand further. Okay. So finally, we're starting to get to where David and I came into this project, and that is if you have C of alpha is just the count of the number of maximally expanded alpha trees for any given alpha. And I want to point out here that I'm actually using alpha in two slightly different ways. On the one hand, it's a word in this language of zeros and ones, but when it comes to talking about alpha trees, it's just sort of a placeholder for the name of that type of tree. Like I never refer to them as the 0011 trees. It's just, it is an alpha tree where the alpha is blank. So just be mindful that I'm abusing the Greek letter here, kind of using it in 2 slightly different ways.
So the alpha is the word that you have a 0
on the labels,
each of the
on the leaves. Yes.
And so, but it's cyclic. So 0011 and 0110 would say.
Right. So if you can choose just cyclic versions of the same word, and you would expect to get the exact same count. And you could also then expect, for example, if you did some kind of reflection, if you took like a chiral version of your tree, because remember it's planar, then you would expect the same kind of count to happen there, which is one of the results from Poirier and Tradler. So then I defined that we have this definition here with a C with the subscripts, that is counting the number of maximally expanded alpha trees when your word looks something like this. It's an O followed by a block of ones, an O followed by a block of ones, and so on. And because you can do these cyclic rotations, you can take any word that you want to and turn it into this form. You are allowed to take these L values to be 0. So if you have consecutive O's, you just take the L sub 1 or L sub 2 to be 0 in that particular case. We don't consider a couple of cases, namely because there are no alpha trees associated with the word that's just an O, and we don't have alpha trees when it's just a bunch of ones. If you try to create an alpha tree that's just a bunch of ones, you'll find that you run into a contradiction. So we can always assume that there's at least one O in the labeled leaves for our alpha trees. And so this is where we came in. This is where David and I kind of came in. So one of the results of Poirier and Tradler is that they found a recursion for this C of alpha function. So they're trying to count maximally expanded alpha trees, and they had some results when the number of indices in the previous slide were 1 and 2. And I think David and I looked at that and they're like, that's a recursion. We could probably do something with generating functions. So that's, again, the part where I said, I don't know what an acycloid polyhedron is. It's because I didn't have to. I could just start from here right? Use that as a definition of this function and just start computing. All right, so one of their results that they had was for two indices, that it's related to a product of Catalan numbers, right? So you've got this like rational function in L1 and L2 times two binomial coefficients. And another result from 2025 was a generating function in the case where you only have one index. And again, you can see that's related to the Catalan numbers, right? So the Catalan numbers seem to be showing up in several places here. So our one of our main results was that we started off by defining a generating function for several indices where you fix all but the first one. So this is a generating function in a single variable. So you fix L2 through LK, and then you're just trying to figure out if we can give a count for C sub n comma L2 through LK. So the L2 through LK are fixed, and then the n value, the first one, is the one that's allowed to sort of roll around. And our result here was that this has a very nice form where you have these two polynomials that satisfy some nice properties, like they're all the coefficients are integers. If you sum them together, all the coefficients end up being even. Their degrees relative to this power of t down at the bottom is less than that, and you see that the Catalan numbers will likely show up. They're going to show up again when you try to compute this for any one specific example. So that's exactly what happens. We can compute the value of that polynomial q, and by solving this matrix equation, we can come up with a formula for C1 of L1 through LK. Again, this is in the case where you fix the value of the indices, the second and beyond indices, and you only let the first index value go through. And you get a linear combination, an integer linear combination of Catalan numbers. So it seems to fall sort of along the same lines of the forms that they were seeing when they were computing for CL1 and CL1L2. So then after doing this for a single index while everything else was fixed, we decided, why not go for broke and then just come up with a generating function where you don't fix anything at all, in which case you have to deal now with k different variables. So this is a jump forward, right, into try to get ambitious and really try to find a formula that works for any and all subscripts, right, not just like a fixed block of them. And so in doing so, we're able to find a relationship between these multivariate generating functions that follows from the result of Fourier and Traveler. And so after seeing this relationship, we wanted to see if maybe we could at least recover their results, right, by taking this generating function viewpoint. And so the corollary here that we obtained from that recursion is that C2 of x1, x2 has this very nice form. C3, you can see, is already starting to get harder to deal with, where we have this variable substitution here that C1 of xi is 1 plus ui. So if you do the substitution, you get some nice forms in the C2 and C3 case, but it starts to get out of hand very quickly. It's hard to figure out what happens next. And that's kind of where we are right now. So you can use Lagrange inversion and Dugall's theorem on hyperdimensional functions to recover the formula for two indices. And then if you use Lagrange inversion again for three indices, you'll notice here that I put plus dot, dot, dot. And that's because there are two more terms in this summation that look very similar to this. I really couldn't make it fit on the slide. And it also shows just how bad the formula starts to get even at the three case. I tried to put this into Mathematica in so many different ways to see if maybe it would finally reduce it to something else. And it crunched for like several hours and then spit out the exact formula that I put in. So it wasn't able to tell me anything. I have not been able to see if this does turn into something nicer. So if you have any ideas, let me know. So you can see that it always starts to get out of hand for three indices. And if you try to do this for four, if you use this substitution down here, you get this sum where there are some terms down here that create a new problem that we didn't have before in the 2 and the 3 case. And that is that this function, let me go back here. In the case of C2 and C3, so in these two functions, you can permute the variables and expect to get the same thing. But if you do that in C4, there are some permutations of these variables that do not give the same thing. And these terms down here are causing that issue. There's sort of like these extra hanging on things that wreck the they keep this from being invariant under any and all permutations. And it seems like it just gets worse, right? So you can have we have this general form of what these generating functions look like, but I don't have a closed form formula for alpha trees for a given alpha value if the number of indices is more than 3. So that's still open. So an alternative approach, and this is incredibly recent. I'm talking about just days ago. So I don't have a complete description here, but I'll try to give you as much information as what I've been doing recently, is to start, rather than starting with an alpha tree and then just expanding until you get a maximally expanded alpha tree, just start with a maximally expanded alpha tree from the beginning and see if we can't build up other maximally expanded alpha trees from that. So here we can begin with 2 maximally expanded alpha trees that have 1 internal vertex. These are actually the only ones that satisfy that. And then once you have these, you generate other maximally expanded alpha trees by adding 1 additional internal vertex. So you can see here that I've taken this leaf and I've turned it into an internal vertex in such a way, one of these arrows is pointing in the wrong direction, so that the statistic there is still equal to 0. The problem here is that this scheme lets you build up more maximally expanded alpha trees, but the alpha word is changing from step to step. So here, what this is really doing is it's counting all the maximally expanded alpha trees that have a fixed number of internal vertices, and they may have a bunch of different alpha words associated with them. So if you're trying to count for a specific alpha word, those trees might show up at different steps in this scheme. And so repeating this procedure n times will give you maximally expanded alpha trees with n plus 1 internal vertices, but you have to be really careful about double counting things. So that one of the tricky parts here has been to try to figure out how to relatively quickly compute whether or not 2 maximally expanded alpha trees are isomorphic. But luckily, because there are so many restrictions, including the fact that they must be planar, one of the things that you can do is you can encode these as strings of characters that describe exactly what the internal vertices look like and what the branches look like. And then once you have that scheme, you can simply check whether or not the string associated with 2 of these maximally expanded alpha trees are exactly the same. And if they're not, then they're not isomorphic. If they are the same, then they are isomorphic. So luckily, there are enough restrictions that you can attach a label to all the different types of scenarios that you can encounter. So I've been trying to write a program that does this, and I got about halfway through. And then yesterday I had to decide whether I wanted to finish that or make sure that my slides were complete for today, because I couldn't do both. So I elected for slides. But if you want to know more about the scheme for doing this and how it's handled, you feel free to talk to me afterwards. I do have some of those papers, my notes really on me. So some concluding remarks here. Well, I'm interested more in figuring out about those polynomials that were associated with the generating functions that were in a single variable. Do they have any kind of interpretation in the context of the problem? What can I say about the following family? It seems like the polynomials that were associated with this family, where you're just increasing the number of indices and making them all 0, that there's some kind of relationship there. What can be said about that kind of thing? Can progress be made in C4? It's actually amazing how much time we've spent on that. I think it's like eaten up. It's now become more than 50% of everything that we've done. Like, we made a lot of progress, and then we're like, we want to have this, and it's just taken an incredible amount of time. So can any progress be made with respect to that? And lastly, is there any other kind of recurrence relations that's satisfied by C of alpha that can maybe be exploited in order to make these counts a little bit easier? You saw the recursions that I gave you, and they lead to these very sort of big relationships between generating functions. And while you can compute it if you're given enough time, you can do it on a computer, it's not easy to see how it is that you write down an actual closed formula. So I give you sort of a general form of the whole thing, but I can't give you an exact closed form. So these are some of the things that we're working on now. I think hopefully see that we're trying to make progress. We still have a lot to work on, but I think that this is the end. So I really want to thank you for listening to my talk, and happy to take whatever questions you got.
Questions? You thought about
using the language of free group with two generators to express the OI sequence to describe, characterize the maximum explaining outcome tree.
So maybe because normally I associate that kind of thing where like you put these edges and then these edges are associated with one of the two with the letters in the language, right? Here the labels are only on the leaves. So I guess the reason we didn't do that is I don't know how that would work.
When you have a sequence of two X, Y, let's say X is O and Y is I, then suppose you have some kind of sequence. Then you have two groups are equivalent for two different sequence. Maybe you can establish some equivalence, like a free group modulo some equivalence.
Okay. I don't. I'm not sure. The closest, I guess, would be what I was talking about earlier, that you can encode these maximally expanded alpha trees into certain strings in such a way that you can tell whether or not they're the same. And that would take, for example, if you had something like 0011, you can take this one and add two edges to it, and then that one gets replaced by an 00. So it has, the string gets longer in a certain way, in a very predictable way. And so I think that's sort of the closest I have to that.
Maybe, so for any word alpha, is there always an alpha tree, or
not all ones. So if you try to construct an alpha tree with
just 0 or 1?
Yes. For other words, you are able to get something. Yeah, because one of the ways you can do that is you can imagine just a single internal vertex, put a bunch of edges coming out of it, whatever it is that you need on the outside of it, and then you can just start expanding until you get something with that statistic being 0.
And the idea of an alpha tree, does this exist? Had this existed anywhere else in graph theory, or did it simply come out of the geometrical problem?
As far as I can tell, it came about from their work. I haven't seen it anywhere else.
No. Other questions, comments?
This is Stanberry.
Excuse me again.
Call about your account. Press 1 if you're available to speak now. Press 2 for voicemail. And a member of our member services will return your call at the best time and number you provide. Please don't make your call may be monitored or recorded for quality and training purposes. Again, press 1 if you'd like to speak now, or press 2 to leave a voicemail. Please leave your name, best contact number, and a convenient time for us to reach you between the hours of 9 a.m. to 5 p.m. Monday through Friday. After the tone, a member from us will call you back as soon as possible. Thank you. Please leave a message after the beep.
Yeah, my name is CJ Mozaki. I'm very busy today. I would say late in the afternoon on Wednesday, I would say around, maybe.
So today, can you do something so we can share your slides? Scriviani? You might technical experts. So see again here. Yeah. Not go. Yes, to get the slides up on our screen. Okay, so you can just share. So you have to do something or he has to share.
Excuse me. Excuse me.
That's it. So, Sergey, can you hear us?
Yes, yes. How to share my screen? I cannot do it. It is written that It is not possible. Melvin.
So instead, can you share your screen with your slides? Or put up your slide?
Might be.
Should figure that out. Right there.
That's just completely motivated.
Yeah.
So, Sergey, do you have your slides on your computer screen?
So I have presentation, but I cannot demonstrate it. It is written that it is not allowed. I don't know.
We give you access now, it should be allowed now. We try again.
Yes. Now it is better. Yes.
So you made him a co-host, I assume?
I just let.
Okay.
Oh, excuse me, I have some.
Oh, word. That is always great. Yeah.
too good not to watch.
Yep. Looks like he's putting it on full screen.
Well, I see in your screen.
You've got the slides, they're just very small.
If you hit Control L, that should make it full screen. But I had already entered my second or second. Yeah.
I think I'm installing something new or just looking at a different program.
Сергей Владимирович, у вас вот эта штука, которая использует веб-камеру, надпись, за ней есть квадратик. Видите его?
Так, это где сейчас?
Выше, выше, выше. Выше.
Сейчас.
Ага.
Так, сейчас. Так, где квадратик?
Вот теперь я ничего не вижу. Запустите демонстрацию.
Так.
Do you have any help in doing this from Moscow?
Александр, где квадратик?
Запустите демонстрацию, я сейчас ничего не вижу.
Так, ну в том-то дело, что я не могу запустить демонстрацию. Вот.
Sends me the slide
Вот.
and then it says next up in the advance.
Вот это. Да, нет.
Так, вот так. Теперь наверху прямоугольничек нажмите.
Так,
Вот наверху. Квадрат.
It's showing up it's control
Выше. Выше.
выше.
Ага.
and alphabet or whatnot.
Вот это зум-митинг?
Нет. Теперь ниже.
Где?
There should be a full
Ниже.
screen option.
Я не вижу. Чуть выше, чуть-чуть.
Да,
Еще выше.
да.
Вот. Вон, видите, в углу. В углу окна.
So those are the slides.
Угу.
Full screen.
Чуть-чуть.
Full screen.
Так. В углу нет, не понимаю где.
Ну вот у вас наверху черточка, квадратик и крестик, правильно?
Да.
Make your
Вот квадратик.
slide full screen.
Квадратик.
Да.
Черточка. Вот это, правое, квадратик.
Да.
Да. Да.
И еще теперь Ctrl-L. Ctrl-L.
Вот. Да.
Молодец.
Сейчас, сначала. Что-то нету так.
Все видно, все хорошо.
Я не... да, вот. Да.